All right, today we're pulling back the curtain on our digital world. We're going to crack open the secret language that powers literally everything from your phone to your car. Let's dive in.
So, have you ever really stopped to think about your phone? I mean, how does it actually work? How does it go from you tapping a piece of glass to launching a whole universe inside an app? It feels like straight-up magic, right? But it all boils down to something surprisingly simple.
See, on our side of the screen, we have a rich world, with text and photos and all the numbers we use every day. But inside the machine, it's a totally different story. Everything, and I mean everything, gets translated into a ridiculously long string of just two symbols, zeros and ones.
And that simple language of zeros and ones is the computer's big secret. It's the bedrock for everything digital, and it has a name you've probably heard before: binary.
But here's the really cool part. Binary isn't just some abstract concept. It's a direct reflection of the physical hardware. Deep inside your phone's processor are billions, literally billions, of microscopic switches. If a switch is on, that's a 1. If it's off, that's a 0. That's it. That is the entire alphabet for every digital device on the planet.
Okay, so if the whole alphabet is just 2 letters, how on earth does a computer understand all the numbers we use every day? Well, let's take a look at how it counts.
Here's the catch, though. Computers don't have unlimited space to think. They have to work in these fixed-sized chunks of zeros and ones, and each one is called a bit. You've definitely heard of this, like 8-bit video games or 64-bit operating systems. That bit length sets a hard ceiling on the biggest number a computer can work with at any one time. It creates a very real limit. For example, let's take a simple 8-bit system. That's a string of 8 zeros and ones. The absolute biggest number it can possibly represent is 255. That might have been enough for a health bar and an old arcade game, but for what we do today, we're going to need a lot more room.
And this is where you can just see the insane leap in technology. A modern 64-bit processor, like the one probably in the device you're watching this on right now, can handle numbers bigger than 18 times quintillion. That's a number with 18 zeros after it. That mind-boggling scale is what makes all of our complex software even possible.
Okay, so computers can store numbers. Great. But the real action starts when they have to do math with them. And you're going to be surprised at just how familiar this whole process looks.
It is almost identical to the addition you learned back in elementary school. Seriously, you just line up the numbers, you add from right to left. The only new rule you have to learn is this. If you add 1 plus 1, the answer is 0, and you carry the 1 over to the next column. That's the entire game.
But this brings us right back to that problem we talked about, that fixed limit. What happens when a calculation spits out an answer that's just too big for the number of bits the computer has to work with? Let's go back to our little 8-bit computer. Remember, 255 is the absolute max it can handle. So what do you think happens if we ask it to calculate 255 plus just 1?
Okay, so in binary, 255 is just a solid row of 8 ones. When we add 1 to that, it sets off this wild chain reaction. We carry the 1, which makes another carry, and another, all the way down the line. But what happens at the very end? That final carry bit has nowhere to go. In an 8-bit system, there is no 9th column. This is what's called an overflow.
And this is where it gets crazy. The CPU, the brain of the computer, doesn't throw an error message. It just drops that extra digit. It vanishes into thin air. And what's left is a string of all zeros. So the computer confidently reports that 255 plus 1 equals 0.
Yeah, you can imagine how that could cause some pretty serious problems.
And this is not just some weird theoretical glitch. It literally happens to the entire internet. The original internet protocol, IPv4, was a 32-bit system, which gave us around 4 billion unique addresses. And a few years ago, we used them all up. The solution was essentially a planned global-scale overflow. We moved to IPv6, a 128-bit system that gives us around 80 octillion addresses, a number so big we're not going to run out anytime soon.
So we've got positive numbers covered. But what about negative numbers? I mean, how do you even write less than 0 when all you've got are on and off switches?
Well, engineers came up with 2 main approaches. The first one, called sign and magnitude, is super simple and intuitive. But the second one, 2's complement, is the really clever solution that almost every computer on the planet uses today because it makes doing the math way, way easier. The simple idea was just to use the very first bit as a sign. A 0 at the beginning means the number is positive, and a 1 means it's negative. The rest of the bits just say how big the number is.
It makes perfect sense to us, but for a computer it actually makes calculations pretty inefficient.
And that's why they came up with this brilliant system, 2's complement. The first bit still tells you if the number is positive or negative, but the way the number itself is encoded is special. It's designed so that adding a positive and a negative number uses the exact same super fast process as regular addition. It's incredibly efficient. The process to figure out the negative version of a number might look a little strange, but it's just a simple recipe. You take the positive binary number, you pop a 0 on the front, then you flip every single bit. All the zeros become 1s, all the 1s become 0s, and then you just add 1. That's the whole formula.
And when you lay it out in a table, it really starts to click. You can see the pattern, right? Every positive number starts with a 0, and every negative number starts with a 1. This one clever system allows the computer to do subtraction using the exact same circuitry as addition, which is a massive win for speed and efficiency.
Okay, I know this has been super low level, a lot of ones and zeros, but understanding these fundamental rules is so important because when things go wrong down here, the consequences can be absolutely huge. So, let's just pull it all together. What are the big takeaways? First, this simple binary math is the engine running inside everything you own. Second, those bit lengths create hard physical limits that developers have to respect. Third, clever solutions like 2's complement are the invisible safety nets that make modern computing stable. And finally, a tiny glitch in this binary world, a single misplaced bit, can have enormous, real-world consequences. I'm talking about things like a NASA Mars rover failing because of a simple data error at this very fundamental level.
So we'll leave you with this question. This knowledge isn't just for computer scientists. It's for anybody who wants to create or solve problems. Now that you know the secret language that our entire world is built on, what could you build with it? What could you fix? Or maybe even, what could you protect?